Okay, welcome everyone. So
You can forego
we're,
a long introduction.
we're very happy to have James Lee. So I think everybody in the room knows him. And for the online viewers, if you don't know him, I highly recommend looking at his other videos. Now the floor is yours.
Okay, thanks. So I will talk about uniformization of distributional limits of graphs. And just since some people are probabilists and are we split 50-50 in the room? Almost, yeah. Okay, good. So the talk is split into two, hopefully brief parts. In the first part, I'll talk about unimodular random graphs, and I'll define them and give some motivations. And we have a number of experts in the room on such things. And then in the second part, I'll do something technical. I guess it's a bit switched, unfortunately, for where you sat. But the technical part will be on just on the finite graphs.
Each side will tell what they need to learn.
Yeah, okay. So, good. So first, let me define a unimodular random graph. So again, it's a case that half the people know very well what this is, so I won't belabor it. So this is a random rooted graph. So a graph G and a vertex row with and the model is supposed to somehow, and maybe Russ can say more about this. Russ and David Aldis have a very extensive monograph about unimodular random graphs. But this model is supposed to capture some kind of random models that are kind of stochastically homogeneous in the in the sense that I don't know, maybe a good motivating example is if you take, say, the integer lattice Z3, and then you, with probability P, independently delete every edge, then you get a random graph, which is not transitive, obviously. It probably has no non-trivial automorphisms. But as a random rooted graph, this will be unimodular, which is sort of capturing the fact that it's, even though even though a particular sample looks doesn't have any symmetries, overall, there is some stochastic symmetry. So let me just give, okay, so that's the kind of what it's meant to represent. Let me just give a definition. So this is a random rooted graph that satisfies a mass transport principle, which is actually where the term unimodular comes from. So is it BLPS that sort of first used this mass transport principle? One
use it in percolation, but
one author nodding one the other direction, but
Ulle Ekström used it in percolation.
So okay, but the mass transport principle is very simple. It says that for every functional, so this is a function on graphs and pairs of vertices. So here x and y are vertices in the graph. The following should hold. So here I will just write right here. So the expected flow out of the root of the graph. So the sum over vertices of f, g, rho x. So this is the, so I sample g and rho, and then I look at the sum over all the vertices, the flow that rho is sending to x. This should be, so this is the flow out of the root should be equal to the flow into the root. Say it again?
F is diagonally invariant under isomorphisms.
Okay, so
Or
let me just answer the. I like when people do this. I'll answer the question as if Russ was wrong, but yeah. So the right. So the question is, what is the domain of F? So so the domain of F here, say, is the class of doubly rooted graphs up to isomorphism. So the point is, like, when you see this g, x, and y, I call g, x, y, and g prime, x prime, y prime the same triple if there's an automorphism taking x to x prime, y to y prime. That's a graph automorphism. Does it satisfy your guess? Okay, good. So the point is, yeah, the functional is the functional on. Basically, graphs are, all the objects here, the rooted graphs are considered up to rooted isomorphism. Okay, so that's a unimodular random graph. And then one example, the only one actually that we'll be addressing here, is distributional limits of finite graphs. So if Gn is a sequence of finite graphs, and in each such graph we choose a uniformly random vertex to be the root, so I'll explain this notation in a second. If this sequence of graphs converges in the distributional sense, or the Benjamini-Schramm sense, or in the weak local topology to some random rooted graph, then this is unimodular. So this provides a sort of rich family of examples, distribution limits of sequences of finite graphs, rooted at a uniformly random vertex. And okay, what is this distributional limit? So, right. So this notion of convergence means that the law of balls around the roots. So if I fix a radius, the law of balls of radius r around the roots here converges to the law of balls of radius r around the root here. Again, where I take everything up to rooted isomorphisms. So two balls are the same if there's a rooted graph isomorphism between them. So like computationally, it basically means that as n goes to infinity, any local algorithm cannot distinguish whether it was sampled, whether you sampled here or here, but just by looking around locally in the graph. So okay, so this is this gives a rich family of unimodular random graphs, and in fact, okay, so such a graph is said to be sophic, and it's actually an open problem whether every unimodular random graph is sophic. So whether every unimodular random graph is a distributional limit of finite graphs in this sense.
I don't mind, but I think you
I don't mind.
Why these are unimodular. In other words, why finite ones that satisfy your definition.
In the sense that this is trivial for finite graphs. Yeah. Was that enough? Yeah. So I mean, if the graph is finite and I have a flow, then right, this is just the average flow coming out of a vertex has to be equal to the average flow going into a vertex by, rearranging this sum. Yeah, here you're summing over rho, and here you're summing over x. Here you're summing over. They're switched around. So yes, here you're summing over the first coordinate and then the second. Here you're summing over the second coordinate and then the first. So this is just interchangement of sum and expectation. Okay, and the specific thing that I want to address today is actually sort of special families of graphs. So one that's been considered quite a lot are distributional limits of finite planar graphs. So in fact, this is what motivated Benjamini and Schramm in the first place to define these sort of distributional limits, because there are models of random surfaces coming from 2D quantum gravity and related studies where you want to consider kind of very large random triangulations. And then in studying those things, they decided sort of it's nice to associate a fairly simple limit object to a sequence of such things. And well, there are lots of experts on the room. In particular, Tom has been doing a lot of beautiful work on these things. Already here, there are lots of interesting things that happen. So let me just tell you the first result, which is the Benjamini-Schramm recurrence theorem. And my my goal is eventually to relate this to their theorem. Okay, so what is their theorem? And then so Benjamini and Schramm. So if G rho is a distributional limit of finite planar graphs, with uniformly bounded degrees, then G is almost surely recurrent, which means that the random walk in G almost surely returns to its starting point infinitely often. So that's the okay. So that's a theorem they proved. One unfortunate thing about this theorem was that so in these models coming from 2D quantum gravity, sort of I talked about these at a lunch a few weeks ago, but sort of say like things like the uniform infinite planar triangulation. Experimentally, one can so you do experiments and you run a random walk for a long time. It appears that the green function is diverging, and you can in fact see the quantitative rate. But it was unproved, and unfortunately, this doesn't suffice to prove that, say, that UIPT is recurrent, because the degrees here are not uniformly bounded. The degrees in UIPT are unbounded. So this was around 2001. So then some other Microsoft alums in 2012, Karel Gorevich and Asaf Nachmias, showed that the same thing holds even if you weaken the uniformly bounded degrees to the fact that the degrees have exponential tails. So so this sort of conclusion still holds when you have something like this for some constant c. So the probability that the degrees are not bounded, but they fall off very sharply. And this is surprisingly delicate in the sense that this is almost, this is almost the best kind of thing you can put here. So there are graphs with, in fact, the best, so for one consequence of what I'll say today is that you could improve this slightly. You could put like log t, you could, such tails still suffice to get almost a recurrence. But anything where you can put log t, log t, log t, and so on. But anything slightly worse than that, there are examples which of things where the degree of the root has that law, but they're almost surely transient. So anyway, so the point is, this is really pretty sharp and kind of delicate. And how do they prove this? So what's the so you use the relationship between recurrence and effective resistances. So I guess let's say it this way. So G is recurrent if and only if the effective resistance from some fixed node, let's call it rho, to infinity is infinite. So a random walk is recurrent if and only if the effective resistance is infinite. Instead of defining effective resistance, let me just restate this condition in a way that will prove.
Does recurrent mean they just step on the same vertex with probability 1 or something?
Yeah, it says that you'll return to your starting point with probability 1. And so so this is, so you can look in, for instance, in Russ and Yuval's book for at least 1 to 3 chapters just about this phenomenon. But one way to restate this, which is, say, using duality, is in terms of extremal length. So the idea is to look over all length functions on the edges of your graph. So you assign lengths to edges. The lengths give you a shortest path metric on the graph. And then you can define balls in this metric. So, okay, let me just write down. So it's a set of all vertices such that the distance according to the length is less than or equal to r. I'm writing it this way for a reason. And then here's a fact that G is recurrent if and only if there So exists a length function such that okay, so the L2 norm of the lengths is bounded, and every ball in the graph is finite. So for all x, for all r greater than or equal to 0. Okay, so this is just a reformulation of the effective resistance condition. That there exists a metric which has bounded area and which makes all the balls in that metric finite. Do you agree with that, Russ or Tom or Yuval? It seems correct. Yes, should be correct. It's not essential that it's correct or not, but I was going to write the standard definition, but I kind of like this one better for what I was going to say. It's 90% correct. Yeah, it should be good. Okay, so right, if every infinite path has infinite length, then it means all the balls are finite. And if all the balls are finite, then every infinite path has infinite length. Okay, good. So I was mentioning how you prove these things. So basically, you say that finding a sufficiently nice geometry on the graph suffices to prove that things are recurrent, and then you use something. Well, now you need to endow these things with some geometric structure. At the moment, they're just graphs, but they're planar. So then you use the circle backing theorem, which says that that every planar graph. Let me just draw a picture. So every planar graph is the tendency graph of some circle packing. So Tom actually has a very nice talk that's online here about circle packings. I almost crashed driving to Banff, not to Banff, but to Vancouver, because I watched it in the car. But not because the talk it was a good talk. I just meant it was so good that you shouldn't watch videos in the car. That's the basic conclusion. So you basically these results use the circle packing theorem, and then from the circle packing construct such a length. That's the basic outline. The circle packing endows your graph with some ambient geometric representation, and then you use that to construct this metric. And okay, so what I will talk about now, we're almost to the end of the first talk part. Sorry, is kind of just a different approach to this, which is instead of considering ambient geometric representations of the graph, just to kind of stick with this setup where we just think about intrinsic deformations of the geometry. So now let me define what I mean by that. So these are, it's a bit of a, it sounds a bit fancy for what it is. It's just a weight function on vertices. But I want to endow graphs with some additional conformal structure. So we have a graph, and then we'll think about non-negative weights on the vertices. Okay, I'm calling this a conformal weight on the graph. And then given such a weight, you can define the lengths of paths. The length of a path is the weight of the vertices in the path. And then given the lengths of paths, you can define a path metric. Okay, so this is the induced path metric. By the way, I mean this is the same setup as over here, except here I have lengths on edges, and here I have here I'm putting weights on vertices. You could define also vertex extremal length instead of edge extremal length, and in the bounded degree case, there was not a difference between the two. I mean, there's a difference, but not an appreciable one. And then again, you have balls in this metric. And then once you define that, you can define let's say a unimodular conformal graph. Okay, so this is a graph and a root and a weight. And I don't want to belabor this point, but so this triple should be uniform. This should be unimodular as a marked graph, in the sense that if you want to update this definition so that it applies, then you need to increase this class so that it contains also weight functions, and then you need to change the definition like this. Okay, so that's the definition of a unimodular conformal graph. And again, if you have you can define I mean, you can just use it doesn't really matter, but you just use an L infinity metric on the weights to endow this space with a topology. If you want to talk about when some weighted graph converges to some other thing. But this is not what's so important. Here's now the definition, sort of the key definition I want to introduce, which is this conformal. Okay, so the conformal growth exponent. I want to think about finding sort of deforming the geometry of a graph so that it has some nice properties, even though the graph metric itself might not have those properties. Circle packing is one way you could do it for a planar graph. Okay, so here's the definition. So given a random rooted graph G rho, let's define a unimodular random graph G rho. Let's define the conformal growth exponent in the following way. It's the infimum over all conformal weights on the graph. When I say that, you have to think about it. What it means is that it's the infimum over all triples G rho omega, such that this is a unimodular conformal graph, and G rho has the same law as G rho. In particular, while it looks like this is a function of the law of this random graph. I'm abusing notation here by writing that it's a function of G rho. It's a function of the measure on random rooted graphs. Okay, so you look over all conformal metrics that are normalized in the sense that they have sort of unit area. And then I want the growth. I want to get the best growth rate of balls. So let's take the limit as r goes to infinity of the log of the number of points in a ball of radius r around the root divided by log r. And okay, so this is the conformal growth exponent. I take a metric that's normalized to have unit area in this sense, and then I look at the best degree of growth of balls I can get. This L infinity norm here, this is the essential supremum of this random variable. So it means that with right, so like if I have a bound on this quantity, then it means with probability 1, right, if this quantity is at most d, with probability 1, the ball of radius r around the root in the infimizing metric, or okay, you might have to approach it if there's not a unique optimum. But sort of with probability 1, the ball has at most r to the d points. That's what I just said is not quite true because you're taking a limit and a log. It would have at most r to the d, plus little of 1 points in it. But I'm just saying this controls the size of of a ball around the root almost surely. That's important. Like this part is holding an expectation, but this is really controlling the size of balls everywhere. And so the nice thing about this conformal growth exponent is now that it controls a number of things. So let me give something representative, which is okay. So here is a theorem. So if G rho is a unimodular random graph, with reasonable, okay, let's say with the degree of the root being reasonable. So, yeah?
Just to clarify, the condition that you had on the length metric is that, the sum of the length of the edges is finite, is not implied by this.
No, this is no, that's true.
Okay, and that's okay.
You can this. Okay, so there are relationships between them, but you're right that this is in kind of the big L2 norm, and that was in a little L2 norm, and so you have to think a little more harder to see the relationship. You might. It would be nice, I guess. It would be nice. So if saying, for instance, that the conformal growth exponent being at most 2 implies that the graph is recurrent, because y2. Okay, we don't see y2 yet, so let's just hold on a second. Okay, so if you have a unimodular graph and the degree of the root is reasonable, so reasonable here just means that the tails decay faster than any inverse polynomial. So it's fairly, I mean, somewhat weak. Oh, I'm switched to purple. My apologies. If you don't like purple, or if you prefer your theorems all in one color. So then my claim is that in this case, let's try again. Then almost surely the spectral dimension of G is bounded by the conformal growth exponent. Okay, and by the way, I will say what the spectral dimension is in a second. Like, for everything I'm stating, I'm just assuming that all these limits exist. Otherwise, you should have lim soups and limits all over the place. So this is this quantity. Okay, so this describes the rate of decay of the return probability to the starting point in terms of the amount of time. You can, instead of parsing the definition, if the spectral dimension is d, this implies, not exactly, but in some fuzzy sense, that the return probabilities decay like t to the minus d over 2. So if the spectral dimension is 2, then you get 1 over t decay in the return probabilities, and so on. And by the way, so what's the proof of this theorem, and indeed my sort of interest in this, and the reason I thought maybe one can say something, is this proof is using spectral graph theory, as you might imagine, because right, if you take a finite graph and you sum that up, then that's just the trace of, that's the trace of the random walk matrix to the power t. So it's exactly, if you can say something about the eigenvalues of this graph, then you can hopefully say something about the spectral dimension. And other things like recurrence and so on. Okay, so that's one theorem. And then for this to be interesting, you should be able to say something about graphs that have a small growth exponent. So here is another, this pen is running out. Okay, so here is a theorem that if G is a distributional limit of finite planar graphs, then the conformal growth exponent is bounded by 2. So, okay, so you can indeed endow such a distributional limit with sort of a metric that has quadratic growth. It's not quite exactly quadratic. There is a log correction, and unfortunately, this is necessary. So there are examples where you need if you see that this limit, of course, allows you for corrections that are, r to the little of 1 in your growth rate. So I proved this theorem, but it essentially follows from work I did with John Kellner, Greg Price, and Shenghua Tang in 2009, looking at sort of the spectrum of the Laplacian of planar graphs. So the way we bounded it was basically by writing down a convex relaxation that would provide test functions for the Rayleigh quotient, and it can essentially be interpreted as a statement like this. And there I had, okay, so one problem with the proof of this is that it's sort of very combinatorial and topological. It involves lots of counting arguments and crossing numbers and things. And that seems a bit, well, it's good for some purposes. It's bad for A, understanding the proof, and B, understanding, if it generalizes and sort of exactly what the right setting is. So I felt very, it was very cool when I discovered that in the proof of their theorem, Benjamini and Schramm offered a hint as to how to do this in a more geometric way. So let me mention a theorem which we will prove in a second, in the second part. So if G is a distributional limit of, so let's not look at planar graphs, let's look at graphs that can be sphere packed, that are the tendency graphs of sphere packings in RD. So it's a distributional limit of, let's just say, finite RD packable graphs, then this growth exponent is at most D. So the topology, and things like with crossing numbers and so on, are not the heart of this proof, because I mean here you can go to higher dimensions, and this is actually sort of the proof of this is actually very general. So it applies. There's no assumption on the degrees, no assumption on the ratio of the radii of spheres in the packing. You can have bounded overlap. You don't have to use spheres. They can be any sufficiently round shapes. You don't have to have things being like they don't even have to intersect. You can just say that two things, there's an edge between them if the distance between two bodies is at most a constant times the minimum diameter. So it's sort of like this kind of quasi-conformal notion of a packing. So I'm saying it's kind of very. This is like a very robust, and in fact, even RD is not essential here. Any Alford's deregular metric measure space suffices. So it's using very little of the geometry. So now let me just tell you. Okay, so that was part one. Part two is just a finite statement that implies this. So let me give below it a theorem just on finite graphs. So here's the theorem. So suppose G is finite and RD packable, then for every radius R, there exists one of these conformal weights such that, two properties hold. One is that the LD norm of the weights is 1. Okay, so it's a natural condition that's generalizing this one to D bigger than. Sorry. Yes, Russ? Same thing here. It means it's the tendency graph of a sphere packing in R to the D. But plus all the things I said. There will be a constant here. All the things I said go into that constant. So the weight is normalized in LD, and then I want an upper bound on the size of balls, but only for this one fixed radius. So some constant depending on D times R to the D for every vertex. Okay, and that this CD is a constant depending only on D. So this is the finitary statement that implies this one. For every fixed radius, I can find the weight that's normalized, and so that I get bounded growth at that one. It's not even growth, but just a bound on the size of that one radius. And like going from a family of weights to this is just very simple. You just choose choose one weight for every dyadic radius, and then just sum them up with some summable function as the coefficients. And you will lose a log factor in the growth rate, but that doesn't come out here. And like I said, that log factor is necessary. Even for a complete binary trees, you need a log factor. The best you can get is R squared log R growth. Okay, so now the question is how to prove this theorem, and that's where this lemma of Benjamini and Schramm comes into play. And I will give an open question, by the way, at the end, which has some very nice consequences. So one consequence would be that it gives the correct speed of the random walk in UIPT. So this is conjectured to be 1/4, but it's not known. So I'm just saying like these, what I'll say here, there's a sort of like, there's more to do, if that keeps your interest. Okay, so this is the goal.
So to prove this
Yes.
statement, you would need the matching lower bound, or is the lower bound obvious?
No, the lower bound is not obvious, and it's a good question. Let's set it aside for now. So what the, I mean, I didn't tell you the open question. I could just include the lower bound in the open question, and then but
I guess the
in a
open
straightforward,
question is to use this methodology, no?
yeah, I will give an explicit open question, which is sort of just, which like looks like condition 2, but it's slightly different. So now I'll give the proof of this, which is pretty simple. So let's so notice, I mean, this thing is parameterized by the radius, but you could also parameterize it by the cardinality here. So if you wanted to, instead of finding one metric for every radius, you could find one metric that makes sure every set of cardinality n has diameter at least n to the 1 over d approximately. So let's do that. So fix n, and now our goal will be the following. If we have a subset of vertices of size n, okay, so we want to find some weight omega such that if we have a subset of vertices of size n, then their diameter under omega is something like n to the 1 over d. Okay, so this will suffice to give us the, if you transform it, plus condition 1, yeah. Satisfying condition 1, such that this holds, yeah. Otherwise, it would be very easy. You could give every vertex weight n to the 1 over d and go home. But it's true, you need an additional bound. So here's how we'll do it. So we need to use the fact that it's packable. And since I can only draw in R2, let's just draw sort of it's a planar graph. So suppose we have the graph packed in, say, the unit square. I don't know. Looks something. Okay, there's not, okay. There's a graph packed in the unit square. So this gives us a sort of a base conformal weight, which is the very natural one. The weight of a vertex is just the radius of x is disk. That's the weight we start with. And now our goal is going to be to sort of deform this weight. So define some phi that deforms this weight that satisfies the conditions. So think about things like this. And then how are we going to do it? Let's just, let's assume we're in the plane. Let's just put down some sort of hierarchical grids of increasing granularity, right? So, you know, sort of with side length c to the n, where n is ranging over the integers. Okay, so just a sequence of these things. And so now just think about such a set U. I want to define a weight function that gives this property. And so I mean, really the only difficult thing is sort of to figure out at what scale does U exist. Right? So U is some subset of on endpoints. How might this subset look? So by the way, here this was a decrease by some fixed constant factor. So this is a cube of side length c to the n, and it has subcubes of side length c to the n minus 1. Okay, so I mean, there's a set U. It looks maybe something like this, and then, I don't know, it could be some denser sets. And so now there's a decision to be made, which is how much weight, do I want to think about U as being a set that has omega 0 diameter delta, and, or like maybe if most of the set U is in here, I actually want to think about getting this condition by rescaling the metric inside this subsquare. Right? I mean, does this, Russ looks concerned, so. I mean, there's a problem, like there's many points here. So sort of, if I scale up all the weights of all those points, maybe it was, too, I do better if I scale only the weights of things here, but then maybe I lost like most of the diameter of U when I did that. So it's sort of, the idea is I want to figure out at which scale U exists. And so here's a definition that basically comes from Benjamini and Schramm. Let's say that let's give this cube a name. Let's call it Q. Okay, so this this cube is length q. It has a bunch of subcubes that I'll call q prime. And then let's say that, oh, by the way, what are all these points? Sorry, I didn't say what they were. Just think about these as the center of the disks. So those points are the centers of the disks. OK, so say that this is call this a level J feature if q minus q prime is at least 2 to the j for every, there's only finitely many of these subcubes. But let's say it this way. So I take all the subcubes at a smaller scale, and I say that if no matter what, when I remove one, I still have 2 to the j points left over, that's a level J feature. Okay? And the idea here is that if I recurse now on some subsquare, I'm losing 2 to the j points no matter which square I recurse on. So I should be doing something for those points now. That's kind of the idea. And what should I do for these points? I mean,
Sorry, can you
yes.
just one more time the definition?
Okay, so you can I like the word feature, but let's just call this a level J cube if whenever I remove one of its subcubes, I'm still left with 2 to the j points. So no subcube contains all but 2 to the j minus 1 points. Okay, and so if we see this, think about now what we want to do. We want the diameter of this set to be something like 2 to the j over d. Ignore for the fact that this is defined for all j, and we're only doing things for a fixed n. But maybe you can ignore n for the moment, because it doesn't suffice just to focus on a fixed n. But OK, so basically what I want to say is that maybe there are some points inside, and then there are 2 to the j points outside. I need to blow up the diameter of those points. This is what I'm saying. So generically, let's say, the diameter in omega 0 is already delta. Like the diameter in the Euclidean plane is delta. Right? I mean, of course, it's not necessarily the case. Maybe, but let's just sort of say that there's a set of points. There's 2 to the j of them. Their diameter is about delta. So the question is, how much do I need to blow this up in order to make the diameter at least 2 to the j over d? So then I should set w to be, or omega to be, omega 0 times 2 to the j over d divided by this diameter delta. If I do that, then if the diameter was delta before, then now their diameter becomes 2 to the j over d. So I'm going to blow up this entire every vertex in this cube. So maybe say it this way. This for every vertex in this cube, we're going to do this. Okay. I'm just saying. So this is just a heuristic argument which says, OK, I've seen 2 to the j points here. I need to blow them up to have diameter 2 to the j over d. So you do this. And then you can ask, OK, how much conformal weight did we use in this process? So if we sum over all those things to the d, then OK, so it's 2 to the j. Oh, we probably should have made this 1 over d, huh? Oh, no, that was correct. Sorry. Yeah, sorry. It's 2 to the j delta to the d times this. This is a bound on the conform. I'm just using nothing. And the point is that this is a circle packing or sphere packing, and those are the radii. So this is bounded by order of delta to the d, where the order contains a constant depending on the dimension. So up to some factor depending on the dimension, the amount of weight we used, the LD norm of the weight we used for that cube is 2 to the j. So now I can just tell you the lemma of Benjamini and Schramm interpreted in this framework, which is just that the number of it's almost their paper is beautiful, so I'm fine to say it's almost trivial. The number of level j cubes is only the number of vertices over 2 to the j. So the number of level j cubes is at most some constant times the number of vertices over 2 to the j. Right? So this is, it's not hard to believe every time you find one, you throw away 2 to the j vertices. So that was almost the proof. So what does it mean? It means that if we sum over all level j cubes then it's at most the number of vertices over to the j times 2 to the j, which is the number of vertices, which means at least that from weighting level j cubes, we use approximately the correct amount of conformal weight, right? Because if you move this says that the LD norm should be 1. So the sum of the dth power should be about the number of vertices. Does it make sense? It's sort of saying that if we just look at sort of the natural thing to do, there's one thing we have to do. This is almost works. So okay, so this works whenever the set you care about is witnessed at a single scale. In other words, the set has n points, and then say the largest subcube has n over 2 points. Then you see a level, then you see n over 2 points at that scale, and you will weight things appropriately. Does that make sense? Seb?
I'm a bit confused by the sum over j.
So every level j cube is costing me conformal weight 2 to the j. So how much conformal weight am I paying altogether? I sum over all level j cubes, of which there are only the number of vertices over 2 to the j. Every one costs 2 to the j.
There are some over j.
Yeah, okay, so definitely there's sum over j. I already told you have to lose log factors. So I will tell you in a second, when you fix an n, you can save this level. You still have to do this for every level, but you can save this log. I'll tell you how to do it in a second. But you could also think about not saving it, and you do need to lose. You will lose a log factor, which you have to lose. You will lose an additional log factor, which you don't have to lose. But so you're right. If you sum over j here, you will lose naively a log number of vertices factor. But sort of at one scale, this seems to sort of work pretty well. So let's ignore the fact that we will spend, if we do this for every scale, we will spend too much weight. So let's ignore that for a second and just verify that we have we get this condition.
I see, but right now, just to clarify, the only issue is that you made your modification of the phi depends on you, which you definitely.
No, it didn't depend on you. I was sorry, it was my fault because I wrote you here, but this is you take this hierarchical partition of the space, and every time you see a level j cube, this is the weight you put. And by the way, it's true. If a vertex sits, a vertex could sit in a level j cube and in a level j minus 1 cube and so on. Then you should sum the resulting weights up. But actually, just the maximum one will be fine. But so you do this everywhere, and just heuristically, at least for one level, you don't overspend the conformal weight. So let me address the overspending in 1 second. Let's sort of verify now that this should hold. So so now just actually consider the set U. I mean, if everything goes really okay, so I guess there's one other issue here, which is that if you happen to choose a bad grid, then you might get half of you might be sitting outside the square you want to see it in. Okay, so you choose constantly many shifts of the grid so that that's fine. That's no, the main problem would be something like this. So here's the smallest cube containing the set U. And then the problem is that you have, let's say, a few points of U out here, and then most of them in here. And then the same thing, and then the same thing could happen recursively, which is that basically every time you go down the scale, you're seeing a few more of the points of U. So, but now most of them are like this, and so on. I mean, this is a problem in the sense that you don't see this ejection of n points of U. You see this slow ejection of points of view as you zoom in. Okay? Does anybody see why that's not a problem? It's just concavity for d bigger than 1 of this. So it's actually only better if this happens, because now I will get now say from here to here I'm considering some path in U. I want to argue that this path is long. Then it gets blown up by this number of points to the 1 over d, and then the number of points of U ejected here to the 1 over d, and so on. By the way, it's not the number of points of view. It's the total number of points, which might be which is bigger than the number of points of view. But does this make sense? So if you saw all the points of view sort of, if U was contained in a cube of level log n, then you would immediately blow it up by the correct amount, and you'd be happy. So the problem is if it's sort of if you experience U being ejected from sort of slowly, but this is not a problem by concavity. So the point is you will get this much credit in the length, and that's more than what you wanted. So that's more. So that this is the point here is that this is n to the 1 over d, where the ni's are the amount that you're kind of leaving out at every time you zoom in. So by the way, this zooming in process was just you take the smallest cube containing U, and then take the subcube containing the most points of view, and then take the subcube containing the most points of view, and so on. And that also explains how you get rid of the log factor here, because when you can focus on a fixed n, basically you can make it so that, I mean, this concavity is actually helping you if anything non-trivial is going on. So when you focus on a fixed n, you can use the concavity to get rid of the extra log factor. So okay, so now let me. I mean, so that was the whole proof. I mean, relatively. I mean, it's right, and maybe like you see that the whole idea is really sort of this very cool thing where sort of you can there's a definite signal that you get about when you should consider a set of points as like sort of this is when I need to blow this set of points up. And it's when there's no smaller cube containing most of those points. Like,
I'm still a bit trying to understand the formal definition of phi.
Yes, I mean, if you really want to, you could define here the level j weight, and then define omega to be the sum of the level j weights.
But we also want to define, there are also the translations of Q, I mean...
Over j squared, and you do the maximum weight at the, this is only over j, which is at most log of the number of points you care about. And it's probably not j squared, it's probably the other way around, right? So it's log n minus j squared. So I give a lot of respect to, I get at n points, I use the whole weight. Then as the number of points goes down, this has this decaying factor, but it's okay because if I'm paying for things with a bunch of small ni's, then concavity is making up for this.
It's very stupid, but at like any fixed point, even at the fixed scale j, it belongs to multiple q's.
Yeah. So the double wj is just for every x in q. Remember, this is a level j cube. So just for every level j cube, everybody who sits in a level j cube gets its weight, gets this much additional weight, and then you get summed over all of your levels. But yeah, so this is fine. And this is delta sub q, right? This is the diameter of q. So you have to, yeah, I mean, there is another thing which happens here, like you sum together a bunch of things. Okay, but d is constant, so you can pay constant depending on d. So does it sort of?
Yeah, it makes sense.
And when you sum weights, I mean, the second condition only gets better. It's just the first condition that's worse. So by the way, I mean, so what did Benjamini and Schramm prove? By the way, I mean, their main the way that they get recurrence is saying that under the assumption of this theorem, the circle packing of G rho has at most one accumulation point in the plane. That's the so they prove this theorem, and then from known results, it follows that the random walk is recurrent. Yeah, right. So an accumulation point is where the circles degenerate right into So if you have a distribution limit of finite bounded degree planar graphs, then you have at most one accumulation point. And okay, I just thought it's nice that you can think about this as basically saying, yeah, this gives you a recipe for uniformization, because like what's happening in uniformization? If all the circles have about the same radius, then you can just use the background metric. That would be perfectly fine. So what you care about is when the radii are shrinking, but the fact there's only one accumulation point says that the shrinking is a very simple process. It's sort of like there is shrinking to one point, and you just have to keep track of. I mean, you can see it in this argument. You have to just keep track of one. Like the circles are away from this accumulation point. The circles are not decaying.
Could that be in your argument? This didn't appear at all. No, I mean why?
No. I mean this is what they use this lemma. If there are two accumulation points, they will contradict this lemma. So I mean it sort of makes sense that you can. I don't know. You need to blow things up. The only hard case for you is when the radii are decaying, but the radii are only decaying to one accumulation point. And then actually the way you handle this is it's actually, I mean, this accumulation point kind of looks like it's really just one-dimensional. It's almost just like a line. That's actually what the concavity here is saying. That, like.
I have no idea what is this point.
That's the accumulation.
No,
point.
it's the next one.
Yeah, it's.
Oh, that's easy.
Yeah. Okay, so now let me just give an open question, which is such a. I'm a little bit worried that I didn't know how to phrase the question in such a nice way. So maybe it has it might follow from what we just did already. But here's the open question. So in this theorem, can one obtain the slightly stronger conclusion that the graph ball of radius r contains the omega ball of radius of the correct radius, which is the size of the. Okay, so this is for all x and r. And there's a constant here. So what's that?
We're going to have 1, 2, and this would be.
No. In lieu of 2, this condition. So this condition implies 2. I mean, if you have this, then it says that you're bounding this bounds the number of points in this ball by the radius of the d, because it's contained in a graph ball. And this is the cardinality of the graph ball to the 1 over d. So this is a stronger condition than 2. Okay, sorry. You want this to. This is for all r. This is only for a fixed r. So it's stronger means that if you don't care about, say, polylog r factors. But I'm just saying instead of just controlling the size of the conformal balls, you actually control them by graph balls. So yeah. So for instance, a positive resolution to this question would show that in UIPT the speed of the random walk is at most t to the 1/4, and the best boundless known now is t to the 1/3. In fact, it would solve a conjecture of Itai that anytime you have a RD packable graph where the intrinsic growth rate is larger than d, so such that the growth of balls is like r to the k bigger than d, then the random walk is subdiffusive. So the claim would be that if you have a RD packable graph, but the growth rate of the graph metric, this is everywhere, and this is upper and lower bounded by constants, is faster than the intrinsic than the sort of the dimension of the packing, then it must mean that the random walk is moving around very slowly. And in fact, it would give the correct speed estimate, which is what? What should it be? Does anybody know? Okay, so if it's k equals d, the speed estimate should be 1/2. So there's probably a k, and then there's probably a d, and a 2. Yeah, okay. So that's not 2 to the k, that's over 2k. Yeah. So and that would be, at least there are examples matching that for every dnk. If it's the right bound, there are examples matching it for every dnk. In particular, up to issues of bounded, bounded degrees, it's known that in UIPT and UIPQ, the growth rate is out of the fourth, and d is 2. So good. Yeah, you get the correct bound, t to the 1/4. Okay, that's all I wanted to say. Questions? I should say that the main advantage of those of using these metrics instead of, say, circle packings is that, I guess circle packings are beautiful because one of the reasons they're beautiful is because they're unique, if under reasonable assumptions. And in fact, I know that you guys use that property for a number of things, but that also makes them pretty hard to understand because it's just a rigid thing that comes from God, and you don't have any way to think about it. So that's a nice thing about these weights, is that they're really ugly, but you can just you can play with them by hand. You can play around. So
you said that Benjamin and Schramm had a lemma which you wrote in the language for your talk. Did they use some other very different language, or what?
Did they use some? No. They in the proof of a lemma, essentially exactly the statement appears. So they have a hierarchical partition into cubes and so on. They had to go. It's not so clear if you have two accumulation points, you can find take a graph. Take a sequence of graphs that's approaching a graph with two accumulation points. How do you find lots of cubes? That's a little bit tricky. That's where they have these sort of delta S supported points and so on. But they show that every delta S supported point gives you a unique level, probably log S cube. So there's a correspondence between their points and those cubes. This is actually the kind of this is a by the way, this is trivial. You can prove it yourself in 5 minutes. It's not. But still somehow, okay.
Right, this particular implication there is considered the heart of their.
Which one?
That the number of accumulation points equals 1.
But it's
The trickiest part of it.
yeah, it's very short. It's like a paragraph, but it is tricky. Right, it's the they basically say that okay. It's true that it's tricky. I always forget. I had like a mini dilemma last night because I couldn't understand their proof, and then finally it clicked again. But yeah, it's okay. It's called. The people call it, I guess, the magic lemma. But it's I don't know. This at least for me, this makes it seem like when you think about it, say in terms of uniformization, it seems very natural to look at those things. Yeah, and I will say one more thing because you all didn't finish saying, okay, let's go, which is that another advantage of this is, so Itai and Nicolas-Curien attempted to extend the Benjamini-Schramm framework to say graphs that are RD packable, sphere packed in RD. so you can do the same kind of argument, and you can get a bound on the extremal length, where now you consider the d norm instead of the 2 norm for the extremal length. So that works, but that doesn't have any known probabilistic consequences. Whereas this one, I mean, this one gives you sort of d-dimensional lower bounds on the heat kernel from the thing I erased. But okay.
All right, thanks.